Sometimes a solution will converge, but just not as quickly as we'd like it to. And in cases like that, there are some things that you can try to accelerate the convergence process. Convergence can generally be improved by using better initial conditions, such as starting from a previous solution, possibly with the aid of solution interpolation, which we talked about earlier in this lecture. Under-relaxation factors or Courant numbers can be gradually increased, and this can help in some cases, but there's always a point where if the values are increased too high, it can lead to solution instability and convergence problems. Because of that, you should always save the case and data file before continuing to iterate. If a case begins to diverge when you've increased the values of these, lowering the values back down doesn't necessarily cause the solution to return immediately to its previous state. A number of iterations is usually required, and it's often faster if you just read the saved case and data file back in. Finally, the best way to accelerate convergence is to create a good quality mesh with appropriate mesh resolution. Nothing else you can do will be as effective as this in ensuring that the solution converges. As a minimum, the orthogonal quality that's reported in mesh info quality should have a minimum value of 0.01, and the average value for this should be much higher. It's critical for the solution to converge, but the fact that the solution's converged does not necessarily mean that it's an accurate solution. This will be discussed in detail in Lecture 10, so for now, we can just say that the accuracy of the solution depends on many factors, including the order of the discretization scheme that was used, the mesh resolution, the boundary conditions, physical model limitations, geometry simplifications, and whether or not the solution was run in single or double precision.